Hi, my name is Luke, and I will present an overview of the paper Behaviour Discovery and Real-Time Strategy Games using Cooperative Co with Dynamic Binary Tree Decomposition. This is a collaborative effort between my colleagues and me, whose names you'll see on the slides, and we are affiliated with the Centre for Artificial Intelligence and Machine Learning at Edith Cowan University in Western Australia. This presentation will provide a high-level overview of our novel approach for optimizing unit behaviours in RTS games. Real-time strategy games involve gameplay where opposing players control multiple units that interact in a dynamic and real-time environment. The overarching goal is to eliminate your opponent, achieved through effectively micromanaging a team of units of different military types. Developing artificial intelligence systems to discover effective team behavior in RTS games is challenging. The game environments feature thousands of positions for many units, each capable of making various moves. Consequently, standard AI methods that operate or learn through simulated playouts are hampered by the large branching factor found in RTS games. One potential solution to explore these large search spaces is focusing on low-level unit behaviors, allowing high-level global strategies to emerge through the collective interactions between the various units. Cooperative co-evolution is an optimization technique that can be used in this manner, yet has only found limited application in RTS games. In cooperative co-evolutionary approaches, individuals from the evolving populations interact to determine an outcome, similar to how RTS game units collaborate against opponents, where these interactions represent components of a more complex problem. A challenge is to determine how to partition different aspects involved in solving the overall problem into subcomponents, where these subcomponents are evaluated based on their interactions. One particular approach could be to evolve a behavior controller for all units of the same type in the same population, or another could be to evolve individual behavior controllers for all units in their own respective populations. A downside to the former is that this approach may not allow enough behavioral specialization to solve the problem, while the latter can facilitate a great level of behavior specialization, but may not scale well with the introduction of more units. To solve this problem, we have developed a novel dynamic binary tree decomposition approach named the B-tree CCEA that simultaneously evolves the optimal subgrouping of units and behaviors for those subgroups that, when working together, can defeat their opponent. Initially, we attempt to evolve successful behaviors for all units in one big group, the root node of the binary tree, as seen in the image with Pop A evolving a single clone behavior controller for all the units. During the algorithm's execution using the binary tree structure, new groups are allowed to either form via splitting leaf nodes or merging them, creating potentially subgroups of units where specialized behavior can evolve. An example of this on the slides shows populations C through E, each evolving behaviors for their respective groupings of units. The B-tree CCA algorithm operates in four main steps. Firstly, we initialize a population of behavior controllers and then evaluate each of these candidate solutions. And then we have population management, which follows the typical crossover and mutation and potentially allows us to split or merge the existing subgroups. Evaluation and population management loop before terminating after a set number of generations. We evaluated our approach using the RTS game MicroRTS, featuring two opposing teams, an evolving blue team at the bottom of each respective image and a non-evolving aggressive red team controlled by the game at the top of each respective image. We designed 4 scenarios to test scalability. Scenario A with 16 units per team, Scenario B features 32 units per team, Scenario T has 64 units per team, and Scenario D has 64 units plus some terrain complexity. Our experiments compared 3 variants of the B-tree CCA, one that splits populations due to randomness, one that splits via convergence, and lastly one that splits due to a stagnation condition. And we compare these against 2 static decomposition approaches across all scenarios where the different algorithms evolved the behavior for the blue units. We evaluated the B-tree CCA and the static decomposition schemes by evaluating the fitness distribution of the best individuals in the final generation over the course of 30 runs. The B-tree CCA variants splitting via randomness and stagnation perform significantly better or comparable to the statically decomposed algorithms, but never worse in the smaller scenario, as demonstrated by the fitness plot of scenario A on the slide, where the higher fitness scores are indicative of better runs. But as the scale of the scenarios increased, the B-tree CCA variants excelled, as demonstrated in the fitness plot for scenario D. In conclusion, This paper has introduced an effective novel dynamic decomposition scheme, B3CCA, based on the hierarchical groupings of cooperating units in an RTS game that can handle scenarios at a large scale.